Hello, this is Group 7 and our second project. This project was created by myself, Joseph Riddell.
Reed Johnson.
And Aiden Passmore.
How to find inner atomic distance and what it means. The inner atomic distance is the distance between two nuclei in any given material. You can find this distance by using the Lennard-Jones potential energy formula. Total energy with respect to R, which is A over R to the M minus B over R to the N. These come from the repulsive potential formula, which is energy equals some constant A over R to the M, and the attractive potential, some energy A equals negative B over R to the N. And then we can find our equilibrium resting point distance by taking the first derivative and solving for 0. Here is our graph for aluminum using the total energy formula. We can see that this is a Nike graph, as they call it, because this big swoosh here, and we go to the bottom of the valley where we find our equilibrium resting point, which is 0.28 nanometers. And here is our graph for iron, very similar, but this one has a resting point of 0.282 nanometers. How to find the elastic modulus and what it means. The elastic modulus, or Young's modulus, is the material's resistance to deformation. It is usually calculated by stress divided by strain, but can also be calculated using our Lennard-Jones formula that we discussed in previous slides. The equation that we would use is our modulus equals 1 over our equilibrium distance times the second derivative of the Lennard-Jones equation, with 1 over R naught being the equilibrium distance. How to find the bulk modulus and what it means. The bulk modulus K is how resistant a material is to a uniform compression, or how resistant it is to being squeezed into a smaller volume. K can be found using the equation K equals our Young's modulus over 3 times the quantity of 1 minus Poisson's ratio. Poisson's ratio, V, for metals is around 0.33.
All right. I'm Aiden, and I will be covering the interatomic distance, Young's modulus, and Bulk's modulus for aluminum and iron. I'm going to be starting with aluminum and work it all the way through. And for aluminum, the Lennard-Jones energy equation is given as 5.841 times 10 to the negative 10th over R to the 4 or R to the 12th, sorry, minus 2.392 times 10 to the negative 6th over R to the 6th. You then take the negative derivative of this to get you the force, and you find where that is equal to 0 to find the lowest interatomic distance. So it'll be F of R equals negative dE over dr, which would then equal 12, because you would counteract the negative, times 5.841 times 10 to the negative 10th over R to the 13th minus 2.392 times 10 to the negative 6th. And this is going to be multiplied by 6 over R to the 7th. And then when you solve for that, you can add over the 6 times the 2.392 times 10 to the negative 6 over R to the 7th to the other side, and then cross multiply to separate it as 12 times 5.841 times 10 to the negative 10th over over 6 times 2.392 times 10 to the negative 6th. Oops. Equals R to the 13th over R to the 7th, but this all equals R to the 6th. So then R would then equal 2.735 nanometers. And that R is R naught. And then when you're solving for the Young's modulus, you have to take 1 over R times the second derivative of the energy with respect to R. So it'll be 1 over R D2E over dr2, and D2E would be 1 over r times 13 times 12 times 5.184. Sorry, 841. And that's all going to be over r to the 14th minus 6 times 7 times 2.392 times 10 to the negative 6th. All that's going to be over r to the 8th. And then when you plug in r naught for all of that, so you evaluate that r at r naught, it would yield 13.68, which is in terms of electron volts per nanometer cubed. And the way you convert that into gigapascals is by multiplying it by 1.6 times 10 to the negative 19th over 10 to the negative 9th cubed, and that would yield 2.19 gigapascals. And then simply, or getting the Bool's modulus from the Young's modulus is pretty simple, where you multiply the Young's modulus, which I'm going to denote as EY, over 3 times 1 minus 2V, which is the Poisson ratio, and we will be referencing that as 0.33, which is commonly known for metals. And when I plug in our data, it gives me 2.15 gigapascals. All right, and now for the iron. The process is going to be very similar, just with different numbers. Our equation for the energy is going to be E equals 6.427 times 10 to the negative 10th over r to the 12th minus 2.5275 times 10 to the negative 6th over r to the 6th. And it's the same formula to find the interatomic distance. So it's F of R equals negative dE over dr equals 0 is the interatomic distance. So that's going to leave me with 12 times 6.427 times 10 to the negative 10th minus 6 times 2.5275 times 10 to the negative 6th over r to the 7th and over r to the 13th respectively. And then when I solve that for 0, do the same cross multiplication, which I'm not going to show. I get r naught equals 0.2825 nanometers. All right. And then for the Young's modulus, it's again 1 over r times the second derivative, so it's d2r e over dr2. And then that would give me 1 over r times 13 times 12 times 6.427 times 10 to the negative 10th over r to the 14th this time, minus 6 times 7 times 2.5275 times 10 to the negative 6th, this time over r to the 8th. And when you plug R naught in of the 0.2825 nanometers, you get the Young's modulus of 2.24 electron volts per nanometer cubed, sorry. And then when you do the same conversion, where you multiply it by 1.6 times 10 to the negative 19th over 10 to the negative 9th cubed, you get 1.27 gigapascals. And then for the bulk modulus, again, when you divide that by 3 times 1 minus 2 times 0.33, you are given 1.245 gigapascals as your Bool's modulus.
Vacancy is the number of point defects in a sample size. This can be found with the equation E equals N times E to the negative formation energy over Boltzmann's constant times temperature. Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin, and temperature is measured in units of Kelvin.
Hello, my name is Reed Johnson, and I'll be covering the vacancy occurrence probability, which can be modeled by NPD equals NE to the negative ET over KBT. This is little t. We have some constants, so our temperature is going to be equal to a constant of 300 degrees Kelvin. KB will be equaling to 1.38 times 10 to the negative 23, and that's in joules per Kelvin. Our ET is 0.7 electron volts, which is equal to 1.12 times 10 to the negative 19 joules. In order for us to find N, we have to divide the density by the molar mass, and then multiply it by Avogadro's number. And our density is 2,700 kilograms per meter cubed. And our molar mass is 26.98 kilograms per mole. And we're going to be multiplying that by 6.022 times 10 to the 23. And that will give us 6.03 times 10 to the 26 atoms per meter cubed. Now we're ready to go ahead and plug back into our formula. So we have NPD equals 6.03 times 10 to the 26, e to the negative 1.12 times 10 to the negative 19 over 300 times 1.38 times 10 to the negative 23. And that will give us 1.074 times 10 to the 17. And this is the number of defects we could expect in a 1 by 1 by 1 meter of aluminum. Now moving on to steel. And I'd like to apologize. I was using T in the previous example. It should be an F right there. But moving on to steel, our energy required for the deformation goes up to 1.4 electron volts, which is 2.56 times 10 to the negative 19 joules. Our temperature remains the same at 300 degrees Kelvin. KB remains the same, and we find N with the same dimensional analysis idea. So we plug that all in, and we get 8.49 times 10 to the 28 e to the negative 2.56 times 10 to the negative 19 over 1.38 times 10 to the 23 times 300. And you can just go ahead and plug that into your calculator and you get 2.57 times 10 to the 5. And that is also going to be the vacancies we could expect to see in a 1 meter by 1 meter by 1 meter cube of iron. As you can see, the number for iron is significantly smaller than the number for aluminum, which indicates that the aluminum has more defects and will have a lower Young's modulus.